Imagine you're a machine learning engineer, right? You're building this massive moderation pipeline for a huge content platform.
Yeah, a total high stakes environment.
Exactly. So you spend weeks, maybe months, training a supervised video detector. You feed it gigabytes of data, you're tweaking the architecture, and you finally hit like 99% accuracy against content generated by Sora.
Which feels amazing. You deploy it.
Right. You deploy it to production, you go to sleep feeling completely victorious, and then you wake up to find that Google just dropped VO3.
Oh, brutal.
Suddenly, your whole pipeline is just broken.
Yeah.
Your detector's accuracy hasn't just slipped a little bit, it is instantly plummeted to zero.
Yeah, I mean, that is the defining nightmare of modern applied machine learning right now.
It really is.
The classification boundary that you thought was, a mathematical certainty, it turns out to be entirely transient. Because as those frontier models evolve, the artifacts your supervised model learned to detect, they just vanish.
You are literally chasing a ghost. And for those of you listening, since you're deep in the trenches of data science and applied math, that shifting boundary is exactly what we're tackling today.
It's a huge problem.
Right. So our mission for this deep dive is to unpack a really paradigm-shifting paper from researchers at Technion, the Israel Institute of Technology. It's titled Training-Free Detection of Generated Videos via Spatial-Temporal Likelihoods.
Yeah, we're looking at a framework they call STAL, which stands for Spatial-Temporal Aggregated Log Likelihoods. And what makes this essential reading for your work is that it provides a mathematically grounded, completely zero-shot detector.
For fully AI-generated videos.
Exactly.
And just to put up some guardrails around our problem domain today, we are not talking about screening for deep fakes here.
Right, no face swaps.
Yeah, this isn't about someone taking a real video and doing a latent face swap or, altering the lip sync to match new audio. We are purely focusing on detecting completely synthetic content.
Where every single pixel across the entire sequence is just hallucinated from scratch by models like Sora or VO3 or Runway.
Right. And that distinction, it kind of dictates the entire approach, doesn't it?
Oh, absolutely. I mean, if you rely on supervised learning to catch those fully generated videos, you fall straight into that trap you just described.
The overfitting trap.
Right. The model overfits to the generator's specific spatial artifacts. So the moment the generator's architecture gets an update, your detector is basically blind.
Well, okay, someone might say if the problem is overfitting to fake training data, why not just use an image-based zero-shot detector?
You mean like training an anomaly detector purely on real photos?
Yeah, exactly. You train it on real photos, and then you just process the incoming video frame by frame. Like, what's the catch there?
Well, the catch is that frame-by-frame analysis is entirely blind to time. Like, a zero-shot image detector will tell you that frame 20 looks photorealistic and frame 21 looks photorealistic. But it completely misses the fact that the transition between those two frames, totally violates the laws of physics.
It's just looking at isolated snapshots.
Exactly. And prior attempts to fix this by building temporal-only detectors, like the D3 method, they lacked a rigorous theoretical foundation. They just operated on empirical heuristics.
But Stahl fixes that.
Yes, Stahl solves this by unifying the spatial and the temporal domains inside this really strict, closed-form, probabilistic framework.
Okay, let's unpack this. Because to build a detection boundary without ever looking at a single fake video, we have to start by mathematically defining reality.
Which is no small feat.
Right. So let's look at the spatial likelihood foundation first.
Yeah.
How exactly does Stahl evaluate an individual frame?
So it begins by extracting frame-level visual representations using a foundation model, specifically DOV3.
Okay.
And the core of this zero-shot mechanism is that they build a calibration data set consisting exclusively of real videos.
So no synthetic data at all?
None. And from this real-only data, they calculate the empirical mean and the covariance matrix of those embeddings.
Okay. And then taking those parameters, Stahl applies a PCA whitening transform.
Exactly.
And when you apply that transform, you're essentially taking this, this highly stretched, skewed, multidimensional cloud of real-world data points, and you're rotating it to align with its principal axis.
Yeah. And scaling it. So geometrically, you're molding that messy cloud into a perfectly uniform spherical cluster.
Centered directly at the origin.
Right, with an identity covariance matrix.
Mm.
So under those newly whitened properties, the coordinates become zero, centered, and completely uncorrelated.
Which means the representations are now incredibly well approximated by an isotropic Gaussian distribution.
Precisely. And because you force the data into that isotropic Gaussian structure, calculating the spatial realism of a new frame becomes computationally trivial.
Because it just collapses into a formula.
Right. The spatial log likelihood collapses into this beautiful, closed-form approximation driven entirely by the L2 norm of the whitened representation.
You're literally just measuring the square distance from the center of your real-world sphere.
Yeah, it is highly efficient. You totally bypass the need for any complex neural network inference just to get a realism score.
I gotta throw a flag on the play here, though.
Oh.
Well, we are talking about extracting a massive 10^24-dimensional embedding vector from a really complex vision transformer like Dino V3.
True.
Can we seriously just assume that this high-dimensional space naturally behaves like a Gaussian distribution once you widen it? Like, that feels like an enormous mathematical leap of faith to build a whole detection pipeline on.
I know it does sound like a stretch. But the Technion researchers anticipated that exact skepticism, and they provide rigorous empirical proof.
Oh, they actually tested it.
Extensively. They subjected the independent coordinates to Anderson-Darling and D'Agostino-Pearson normality tests.
What were the results?
After whitening the Dino V3 embeddings, over 98% of the coordinates clear the threshold for the Anderson-Darling test.
Wow.
And over 99% pass the D'Agostino-Pearson test.
Okay, so the geometry actually holds up under scrutiny.
It really does. And there's a deeper theoretical reason for this that connects to the pre-training of the foundation model itself.
You mean how Dino V3 is trained?
Yeah. Models like Dino V3 heavily utilize contrastive learning objectives, specifically variants of the info-ends-E loss.
Oh, right, where it's pulling positive pairs together.
Exactly. It pulls positive pairs together and pushes negative samples uniformly apart across a hypersphere. And recent theoretical work has demonstrated that this info-ends-E objective asymptotically induces a Gaussian structure in the learned latent space.
Okay, that is a crucial insight. So the Gaussian behavior isn't just like a lucky break in the data.
Not at all.
It's a direct downstream consequence of the contrastive loss function used to train the vision model in the first place. The math is literally baked into the foundation.
Exactly. It's structural.
Okay, so we have a rigorous, mathematically sound way to assign a spatial log likelihood to a single frame. It proves a frame looks statistically real.
Right.
But as we established earlier, Sora can generate a breathtakingly realistic frame that suddenly, melts into a nightmare in the very next second.
The temporal melt.
Yeah. So how do we mathematically catch that temporal anomaly?
Well, this was the major hurdle for the researchers, because if we look at the raw temporal transitions, like simply taking the embedding of frame 2 and subtracting the embedding of frame 1, we hit a huge statistical wall.
Let me guess. They aren't Gaussian.
They are fundamentally not Gaussian.
Which makes intuitive sense when you think about the mechanics of video, right?
Yeah.
Because raw transitions capture the absolute magnitude and direction of change.
Yes.
But motion in the real world is entirely arbitrary. A camera can pan left, it can zoom in super fast, a bird can fly slowly across the background. You have a massive variance in speed and direction.
Right, so in the latent space, that looks like a messy starburst of motion vectors.
Just shooting off in every conceivable direction with wildly different lengths.
Exactly. And if you run those same Anderson-Darling normality tests on those raw transition vectors, the pass rate drops from 98% down to literally 0%. Zero. None of the coordinates behave like a Gaussian distribution.
Okay, here's where it gets really interesting. The paper introduces a truly elegant geometric fix for this.
The L2 normalization.
Right. They apply an L2 normalization to those transition vectors. They essentially take every raw motion vector and divide it by its own length.
So think about what that does to your starburst analogy.
It strips it. Instead of vectors of all different lengths shooting out into the void, you strip away the magnitude of the motion.
Right.
You're projecting all of those transition directions uniformly onto the surface of a perfectly smooth, high-dimensional glass sphere. You just isolate the pure direction of the semantic change.
And by projecting those vectors uniformly onto a high-dimensional unit sphere, the researchers unlock, honestly, one of the most powerful tools in high-dimensional probability.
The Maxwell-Poincaré lemma.
Yes, the Maxwell-Poincaré lemma.
Okay, let's break down the mechanics of that lemma for our listeners, because it's essentially the linchpin of the whole paper.
It really is. So the lemma states that if you have high-dimensional vectors distributed uniformly on the surface of a unit sphere, any fixed low-dimensional linear projection of those vectors will approximate a standard Gaussian distribution.
So if we try to visualize that in, say, 3 dimensions, like points scattered around the surface of a globe, a random projection might cause those points to clump unevenly, like maybe around the poles.
Sure, in 3D that happens.
But in a 1024-dimensional space, the geometry is so unimaginably vast that the projection almost perfectly forms a bell curve.
Right. The sheer scale of the dimensionality guarantees the distribution. Because the embedding space is so large and the normalized directions are uniform across that hypersphere, the individual coordinates basically behave as standard normal variables.
That is wild. The math literally smooths out the chaos of arbitrary motion.
It does. By simply applying that L2 normalization, the normality tests go from a 0% pass rate back up to almost 100%.
Which means you can now safely apply the exact same PCA whitening transform.
Yeah.
And the exact same closed-form Gaussian log likelihood equation to the normalized transition vectors.
Exactly. It creates perfect symmetry in the algorithm. We now have an isotropic Gaussian model evaluating spatial realism and an identical isotropic Gaussian model evaluating temporal consistency.
It's a beautifully unified framework, but it does introduce an interesting edge case when dealing with video data in the real world.
I think I know where you're going with this.
Yeah, what happens when there's absolutely zero motion? Like if a video holds on a completely static shot, 2 consecutive frames are identical.
Right, so the transition vector is exactly 0.
And you cannot divide a vector by a 0 L2 norm to project it onto a sphere. The math just blows up.
It does, but the Technion team implemented a deterministic fallback to handle that.
Oh, they did?
Yeah. If a transition vector is 0, it obviously carries no temporal information anyway, so it's systematically discarded from the temporal log likelihood computation.
That makes sense.
And if an entire video is nothing but a static image held for multiple frames, no temporal score is defined whatsoever. The method just gracefully degenerates into relying exclusively on the spatial log likelihood score.
Okay, so it's a practical engineering safeguard wrapped around the theoretical model.
Exactly.
So, assuming we have normal motion, we now generate independent log likelihood scores for the space and time domains. But we have a scaling problem now, don't we?
We do, because these two distributions operate on fundamentally different magnitudes.
Right, you can't just average the raw spatial score and the raw temporal score together.
Yeah.
One will completely drown out the other.
This is where the researchers employ percentile aggregation. Instead of using the raw log likelihoods, Stahl takes the test scores and converts them into rank-based percentiles relative to the real video calibration set.
Okay, so the algorithm is essentially asking, what percentage of real videos scored worse than this specific frame or this specific transition?
Precisely. That elegantly normalizes the scales.
But wait, before you calculate that final percentile, you have to collapse the sequence. Because for a given video, you have a spatial score for every single frame and a temporal score for every single transition.
Right.
And the paper explicitly dictates taking the maximal spatial likelihood across all the frames and pairing it with the minimal temporal likelihood across all the transitions.
Yes, that's key.
I really want to dissect that logic. Why not just take the mean of the frames or the median of the transitions?
Well, the authors ran cross-domain correlation analyses to figure that out. They tested various aggregation methods, mean, median, min, and max, and they computed the Pearson and Spearman correlation coefficients between the resulting spatial and temporal scores.
And what did they find?
They discovered that pairing the maximal spatial score with the minimal temporal score yielded the lowest correlations, hovering around 0.55 for Pearson and 0.49 for Spearman.
And low correlation is the goal here, because highly correlated scores mean your 2 domains are capturing the exact same information.
Exactly. One branch just becomes redundant. You want orthogonal complementary signals.
But look at why that specific max-min pairing produces orthogonal signals. Think about the fundamental failure mode of AI-generated video.
Right, temporal melt.
Yeah, when a generative video breaks the illusion, it's rarely because every single frame is uniform garbage. Usually the model generates a breathtakingly photorealistic face, which gives you a massive spatial score.
But a second later, that face blinks sideways.
Exactly, where the background geometry just collapses, resulting in a terrible temporal score.
Right.
If you average the scores across the video, that one photorealistic frame might artificially inflate the final output, completely hiding the bad transition. by pitting the best visual moment against the worst motion transition. Stall basically forces the generative model's biggest flaw right into the spotlight.
It perfectly exploits the inherent inconsistencies of frontier models. And once you isolate those max and min percentiles, the final unified stall score is remarkably simple. You just take the average of the spatial percentile and the temporal percentile.
So theory and geometry are beautiful, but for the practitioner listening right now, theory is only as good as its execution in production.
Of course.
How does this training-free zero-shot math actually hold up against state-of-the-art supervised models on real frontier generation systems?
Well, the empirical validation in the paper is really extensive. The authors evaluate stall across 3 major datasets. They use 2 established benchmarks, video feedback and gen video.
Okay.
But they also introduce a new, highly challenging dataset called ComGenVid.
We really need to highlight ComGenVid because this is where the boundary truly shifts. This benchmark features the newest wave of high-fidelity commercial models, specifically focusing on outputs from OpenAI's Sora and Google's VO3.
And the performance metrics on it are striking. Stall achieves state-of-the-art average performance across all 3 benchmarks.
So it doesn't just beat other zero-shot methods.
No, it outperforms fully supervised models that were trained on massive datasets of synthetic video.
Which is staggering when you remember that Stall's calibration set contained exactly 0 fake videos.
Right.
It learned everything it needed to know purely from the statistical structure of reality.
Exactly. And the ComGenVid benchmark also exposes the exact catastrophic failure mode you mentioned at the start of the show.
The VO3 nightmare.
Right. The researchers highlight that on certain unseen generators, competing supervised detectors experience complete decision boundary inversion.
Wait, what does that look like in the actual metrics?
Their area under the ROC curve, or AUC, drops below 0.5.
Wow, because a random coin flip is 0.5.
Exactly. These sophisticated supervised models are literally classifying fake videos as real more often than chance.
Because they've overfit to the artifacts of yesterday's training data, they are actively searching for noise patterns or, like, spatial glitches that Sora and VO3 just don't produce anymore.
Right, and because they don't find those legacy artifacts, they just confidently label the synthetic video as real.
But Stall doesn't do that.
No, because Stall anchors its detection on the immutable statistics of real-world physics. It never exhibits this inversion. It maintains consistent, robust separation across every single generative model tested.
So what does this mean for the machine learning pipeline? Beyond the sheer robustness against model rot, Stall offers incredible operational viability.
Yeah, the efficiency is huge.
It runs at just 0.22 seconds per 16-frame video. That matches the absolute fastest temporal-only heuristics available.
And it vastly outperforms complex supervised methods that can totally choke a pipeline by taking up to 5.4 seconds per video.
Right. If you're handling real-time moderation at a platform scale, that throughput difference is the whole ballgame.
Absolutely. And the ablation studies further prove how unbreakable the metric is. The researchers intentionally tried to stress test Stall using common pipeline degradations.
Like what?
Well, they varied the frame rate, dropping the input from 24 frames per second all the way down to 2 frames per second.
Oh.
The AUC remained remarkably stable.
Wow. Did they test deeper temporal context, like comparing frame 1 to frame 4 instead of just consecutive frames?
They did. They evaluated higher temporal derivative orders looking at second, third, and fourth order motion dynamics.
Did it break?
Nope. The performance was virtually identical across all of them, which empirically proves that evaluating first-order adjacent frame transitions is entirely sufficient for detecting synthetic motion.
Okay, what about spatial noise? Because social media platforms compress video heavily.
They applied severe Gaussian blur and heavy JPEG compression to the test sets. Stall's accuracy held totally firm.
That's impressive.
They also proved the framework is completely invariant to the specific calibration set used. Whether they calibrated the whitening parameters on the Vatex dataset or MSR VTT, as long as the set contained more than 5,000 real videos, the statistical boundary generalized perfectly.
Okay, let's synthesize what we've covered here. Stall is not just an incremental tweak to an existing loss function.
Yo, not at all.
It represents a fundamental paradigm shift in how the industry can approach synthetic video detection. By leveraging the geometric properties of high-dimensional embeddings and the Maxwell-Poincaré lemma, researchers have taken the chaotic, unpredictable domain of temporal motion and transformed it into a rigorous, closed-form, probabilistic model.
And for professionals managing large-scale detection systems, the value proposition is undeniable.
Definitely.
STAL provides a lightweight, highly interpretable metric that completely bypasses the need to constantly retrain models against the latest generator. It grounds the detection boundary in the physics of reality rather than the transient flaws of artificial intelligence.
Which brings me to a final theoretical prompt for you to mull over as we wrap up today.
Oh, I like these.
So, STAL operates on the premise that the statistical structure of real videos, when properly normalized, is rigidly Gaussian. But as generative models like Sora and VO3 become mathematically perfect at simulating reality, we have to ask a pretty difficult question.
Okay.
Will there eventually come a point where AI-generated motion perfectly maps to that exact same Gaussian distribution? If a generator achieves a flawless simulation of real-world physics in the latent space, does it permanently erase the statistical boundary that STAL relies on?
Man, that is a fascinating problem for the next generation of detection research.
It really is. Something to ponder during your next model training run. Anyway, thank you for joining us on this exploration of the STAL framework. Keep questioning the data, trust your mathematics, and we will see you on the next deep dive.